Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video is for our numerical computation course, and this lecture is on optimization. We will introduce the topic in this lesson. So basically, you guys know from calculus how to find maximum or minimum value of a function by taking the first derivative, right? And then as long as you can take that derivative, you set it equal to 0 and solve for the values of your variable that make that true, and you can use the second derivative to determine the curvature and determine whether that's a maximum or a minimum. And that's a great technique for optimizing a function, okay? And this still applies to our engineering problems with some minor adjustments, right? The most significant of these is that I do have to have a physical limitation on my acceptable answers, right? Composition needs to be between 0 and 1. Mass flow rate needs to be positive, etc. Okay, so we're going to be finding maxima or minima with constraints. Okay. So we're going to be looking at a few of the optimization techniques in this unit. Let's start by just looking at our really simple calculus type problem. So let's say we've got a plant, it's going to make some product, and the profit is going to be the difference between the revenue, how much we can sell that stuff for, and the cost of operating the plant. Okay, right, our purchase price of our equipment, all of our utility costs, we've got to pay our employees, etc. Okay, so that's going to be our profit. And if I do this, let's say I came up with, in terms of a mass flow rate M, the profit is 7.3 M minus 0.025 M squared, okay, where M is in kilograms per hour and P is in US dollars. So let's, for this hypothetical plant, what is the mass flow rate that's going to maximize my profits, right? That would be one of the things we might wish to do in a plant. So we know how to do this using calculus, right? So you find the first derivative, dp dm, in this case 7.3 minus 0.05 m. Then you're going to set that equal to 0, and you're going to solve for m, and we end up with 146 kilograms per hour is the flow rate that's going to maximize this. Okay, so good. That's a positive number, so therefore it's at least physically possible. But what if our plant is only capable of producing 100 kilograms per hour? If that's the case, then this is not a reasonable answer. And so therefore we're going to need to evaluate those endpoints, right? 0 and 100 as values of m. Go back to your function and see whether or not this is going to be reasonable, or you could use the derivative and look at the slopes and see if there's been a slope change between there. Is this an increasing or decreasing function, right? So logic can help us figure out which of those values would be the maximum reasonable answer. Now normally, again, we would use the second derivative. In this case, it's negative, and so therefore we know that, yes, that 146, if that's possible, is going to be our maximum value. But, okay, this was an easy little problem. What if the derivative is difficult to work with? So there are several different things we might do. The first of these, we just finished learning how to approximate derivatives. And this actually is a good technique in this case. You can build a table of values for small delta x, small enough that works for what you're trying to find, okay? And look for where you get the derivatives changing signs, right? And then you know that in between there, it's going to be your 0, what we were looking for analytically using the calculus technique. There are also trial and error approaches, right? You could just start randomly trying numbers and, keep subtracting the region as you get closer and closer and hone in on what that maximum or minimum is. It's kind of scattershot, but you could do that. Of course, you could do this trial and error type approach using Excel's built-in tools. And we will be looking at that also. There also are times though when we have functions of multiple variables, or if you have multiple functions that you want to find the common extrema for all of those. Okay, so maybe the intersection of those multiple functions is going to be a line, and then you want to find on that line of intersection or curve of intersection what the maximum is, right? So the problems can get more complex. You covered this in Calculus 3, and if you can evaluate all of the partial derivatives involved, those actually work great. But again, that's not always a reasonable thing to do. So there are numerical techniques that you can use, but we are not covering. They are more advanced than what we're going to get to in this course. If you need them in the future, my favorite resource for these, because he has sample code for you that you can use as a starting point, a book on numerical computing by Richard Davis. He's at the University of Minnesota, Duluth, and that textbook is actually pretty good for finding code that will do these more advanced complex problems. We will, however, look at this in one of the next lessons here, using Excel Solver. Okay, now again, with anything using Excel's kind of trial and error techniques, just like when we were looking at solving numerical or nonlinear equations numerically, you have to have a good first guess. And when it's in a complex space, that can be pretty hard. So you've got to have a good idea of what the first guess is for this technique to work, but when it works, it's pretty easy, so we will look at that. So that concludes this introduction to optimization, and come back for the next lesson where we will try out these various techniques. Thank you very much for your time.